So a number of questions have come in, and so this is to actually look at some of those questions, and then we'll have an open panel discussion later. So question one, is there only one solution to replace fossil fuels? Is there a magic technology? Simple answer, no. So here's the map of what I call scenario F, which is like the hybrid scenario where what have we learned? Fossil fuels, and this is the task that we've actually used them over 1 year in a global sense. The vehicle transport fleet, self-propelled vehicles, let's break it up. So all short-range vehicles become electric vehicles, and all long-range or heavy vehicles should be hydrogen fuel cells. Aircraft became biofuels. So accounting for a 10% transmission loss between the generation of power and the point of application, we will need that amount of electrical power to do those tasks. Generating electrical power with fossil fuels looked like that across the year of 2018. Heating using gas and coal-fired steel manufacture was that. So if we were to replace all those with renewable alternatives and accounting for a transmission loss, we need a little under 20,000 terawatt hours. Petrochemical plastics went to bioplastics, and petrochemical fertilizer had no viable replacement, which suggests that our food should eventually evolve back into small-scale organic, possibly supported with some kind of industry. Sum all those things together, and that's how we get our 36,000 terawatt hours for the calendar year. Now, we're not going to use fossil fuels anymore, oil, gas, and coal, so there are our power generation options. I unpacked nuclear in those sections there, and I looked at biomass and biomass to waste and biofuels in those sections. Power storage was required to manage intermittency of wind and solar in particular. We'll discuss that later. In 2022, the IEA released a study that made a prediction in the year 2050, what would the energy split be? That's this column here. So I've actually used that in conjunction with some of my own work to work out an energy split. Wind and solar represents about 70% of the total split. So based on those assumptions and using some of my own assumptions, I've come up with this split of how we think we're going to go forward. I also collected some information with regard to the performance of energy systems across that group in the year 2018 in terms of what did they deliver and what our operating hours did they actually generate power for. So based on that, the average metrics gave us the number of average stations we would need to meet those 36,000 terawatt hours, and that's how we got the 586,000 power stations. The number of technology units were assembled. This is the actual size of the physical units that now need to be replaced. Electric vehicles and their batteries, that's that part there. Hydrogen fuel cells. Now, hydrogen fuel cells is a relatively small number of vehicles, but they do most of the work. And for that reason, the hydrogen economy might have to take priority over the electric vehicle system. Turbines, well, that's the estimates and calculations there. Solar panels, assuming that all solar panels are 450 watt commercial grade. And the stationary power buffer down the bottom. There were two calculations for that. One was the 2,000 terawatt hours. The other was for 48 hours plus 10%, which was 158 terawatt hours. Both calculations were used and shown. Okay, so everything has its place. There's our electric vehicle fleet. There's the hydrogen economy. Heating of buildings, steel manufacture, and that's how we get our 36,000 terawatt hours. Aviation should go to biofuels, but how much? That's a very serious question because there's sustainability problems there. And petrochemicals became replaced by bioplastics. Again, what can we actually harvest from the environment? And that's our power split if we were to apply the IEA energy split. And that is the power storage buffer, which we'll come to later. This is the elephant in the room. This is requires the most resources. And if we don't meet this challenge properly, wind and solar are actually not viable. So there are no magic solutions. Everything is needed. Each of the existing proposed systems also face, they work quite well on a small scale, But when you want to scale them up to be available for everyone, they all face logistical bottlenecks of some sort. What battery chemistries were used? In the first generation of the study, only one chemistry was used because I did not able to get an estimation of the battery market share. But in 2022, the IEA released this nice report, which actually gave an estimate of not only the metal content in terms of kilograms a megawatt for batteries and all solar panels, but they also gave market share estimates. So here is the market. This is wind turbines. There are 4 basic wind turbines. In the year 2040, this is what is believed the market will look like. So the market share, and we also have for each wind turbine metal content in terms of kilograms a megawatt. So we have the needed volume, we have the needed capacity for each system. We have the average performance of your average wind power system array, which gives us the number. And then the number is then projected onto market share for the different unit types. And each unit type had a metal content. So all of that was summed together. So that was done for, there's about 30 tables of numbers here. They are being published. So I'm giving you like a summary across the top. Here is light duty vehicles and heavy duty vehicles, the cathode chemistries in their batteries. And that was able to give this situation here where I could make these judgments with regard to what the market share might be in the future. All of those chemistries were used. At the same time, the same thing was done for power storage chemistries. Again, the same estimates from the same report. And because we had the metal content for each chemistry, we're able to project how much capacity would be required for each chemistry, and thus can work out the metal content required to deliver those chemistries in those volumes. And all of that could be summed together. So this is for stationary power storage. So that got to this point here, where we can look at, say, onshore wind turbines. How much metal will we need and what kinds? Offshore wind turbines, solar panels. We're going to construct a number of nuclear power plants, hydro power plants, geothermal power plants, electric vehicles, less their batteries, hydrogen fuel cells. I only had the data for the platinum in the cells, not for the rest of the vehicles. That's okay, we can move on. And the metal content and electric vehicle batteries. And the last column is stationary storage for 4 weeks of wind and solar. We also have the metal content for 48 hours plus 10%. I'm going to talk about shortly about which of those we should probably go with. However, these are highly dependent on the size of the buffer that we need and what form it would take. Is it hours? Is it days? Is it weeks? So how do we compare to other studies? Why am I looking at this one? Net Zero America. 3 energy experts took the time to publish in a Finnish newspaper to a critique of my work, that my work wasn't very good, and they used this report to do it. So this is why we're looking. Net Zero America. This is a nice report that was actually put together. It's quite well presented, and they've done a lot of work. I question some of the assumptions underneath it. Here we go. So what they've got is a series of scenarios. They have a reference base case all the way out to 100% renewable. My work looks at the reference case and the 100% renewable, and I've done it just for the year 2018. This report has actually made projections out to 2050. And so this is for the United States only. So they've got, for their various different scenarios, they have a share of power generation as well as power consumption. So there is my reference base case, and there is my transition. This is for the year 2018, which is only in the left-hand side of that graph only. So what they've done here is they've worked out that supply and demand must balance, and it must balance to within a millionth of a second. And demand goes up and down. This is the solid black line. And there are times when, in terms of power generation, demand exceeds supply, and sometimes supply exceeds demand. So when it does exceed, keep that supply and then project it into the peaks where it underperforms. That's the idea. And so they have a whole series of things of generation across the top and then load across the bottom. And it was this is how they got 5 to 7 hours of power generation for battery power generation using other technologies. So what they've done here is you have a series of ups and downs. Each day and night it goes up and down, generation versus load, and it's done on a day-to-day basis. What this does is looks at the day-to-day variations of demand. It is not looking at the long-term seasonal variations in the weather. And what they've done to actually absorb the excess power, you've got direct air capture, electrolysis, and electric boiler. Now, direct air capture of carbon uses the electricity, but it doesn't use it in a way where it can be recovered later. And the electric boiler is, as I'm reading this right, you have electricity, you're going to send it to another part of the grid and use it to generate electricity again with an efficiency loss. We're not going to recover it later. We're not storing it for a long period of time. So this is actually not a buffer. What you're doing is you're consuming extra energy. And the third option is making hydrogen using electrolysis. Let's look at that. So it's about 55 kilowatt hours to make a kilogram of hydrogen at the moment. I've assumed 50, assuming future innovations of efficiency. And then you need 2.5 kilowatt hours a kilogram to compress that hydrogen into a 700 bar tank. So let's say 52.5 kilowatt hours to make a kilogram of hydrogen. When you recover that hydrogen, we're getting 15 kilowatt hours out the other end. So we've got about a 27% efficiency for energy storage. You could say that that energy is being consumed in the hydrogen economy. What we are not doing here is an effective buffer. I'll talk about the size of the buffer next. So this study accounts for the smoothing of short-time fluctuations in demand only. It does not allow power steady supply for longer-term lulls in wind or solar radiance when it comes to wind and solar. I will show that next. Methods proposed to absorb variation in wind and solar don't actually store the energy for later use, except for the possible use of hydrogen, which is only 27% efficient. And if that's the case, we should use another method of storage anyway. The application of direct air capture of carbon does not assist in the delivery of stable power through the grid. You might be consuming the energy in an appropriate way, but it does not actually help when the grid underperforms at a later date. The entire study is also based around that all renewable energy transition assumptions are made in an era where fossil fuel consumption is a reality and fossil fuels have expanded in capacity year on year. When those fossil fuels or economic growth for that matter declines, that invisible subsidy will turn into a penalty. I don't believe that study is accounting for that. Raw materials required for feedstock manufacture of all units are just assumed, with no calculations of needed quantities of metals. So how big should this buffer be? Well, in 2021, here's a map of Europe. Every European nation had an exchange with other European nations. Some were transferring power to support. Every single one of these were using it to balance supply and demand, usually using some sort of fossil fuel system. You might notice Germany is supporting a large number of countries. So all networks are balanced by the external use of other external networks, usually fossil fuels. This was a study done by Ewan Mearns in Spain in the month of September 2015. Look at the, this is for wind and solar thermal. Look at these massive peaks. You have these massive peaks and then long periods of lulls. So we will need, so this is 2 months of marked by periodically wind-free conditions of Europe, Northern Europe. So they had these massive swings of up to 48%. So if we had like a steady level going through that, the peaks would then have to be kept and stored and then released slowly through the lulls. And these things last for days, not hours, weeks sometimes. Here's another study, again by Ewan Mearns. This looked at concentrated solar power in Spain. They compared 2 months, one in winter, one in summer. if we were to have a steady 670 megawatt baseload of power generation across the whole year, we'd need some storage in summer, which surprised me, and some storage in winter, like a lot of storage. How much storage? Well, you'd need approximately 260 gigawatt hours of storage would be needed to cover the shortfalls of November alone, just November. That's 16.2 days of buffer capacity. Now, here's the interesting part. You'd have to collect it in summer. You'd have to keep it to 4 to 6 months and then release it slowly over winter. Now, this is in Spain, where the sun is actually pretty good. Here is the solar radiation in Germany in the same year, 2015. It's not rocket science. We're seeing more solar radiation in summer compared to winter. So let's say we're going to have our steady power capacity about halfway. Now remember, this is 35% of the power grid going forward. Anything over that dotted line would have to be kept and stored. It's a double the capacity there, but it goes for months. Every month for 6 months, we have to be storing lots and lots of capacity. We then have to store it for about 4 to 6 months and then release it slowly over the winter period to maintain the even proportion. To date, all renewable power systems are balanced by something else externally, usually fossil fuels. Here is a study, again by Ewan Mearns and Didier Sornet. This is in Switzerland about their solar energy plan. The dark line is demand. And then the yellow is solar power that's captured during the month of July. You might notice every now and then you have these peaks that are oversized. The size of those peaks going past demand will increase short-term requirements for power storage buffer, and you would have to keep that power for 4 to 6 months. So when we say we need a power buffer, how big should it be? 4 weeks, I thought, was a very conservative method for getting these long-range variations. What the real number is, I actually don't know, because I don't believe the work's been done. So wind, so the UK Parliament did a study on wind, and they found power production was so erratic it couldn't be predicted. And they had a few storms come in, so it was actually really variable. This was the actual wind power that was delivered in that time period. It was highly variable. Look at those peaks and look at the periods of lulls. So that data was then added to 4 other nations: Sweden, Denmark, UK, France, and Germany across the September-October period of October 15. This is Ewan Mearns again, excellent work. So you've got these massive peaks and then you've got lots of lulls. But when you're seeing a peak in Denmark, you're also seeing it in Sweden, UK, and France. So the idea that you could use one country's grid to balance another country's grid is not going to work when they're all peaking at the same time. In terms of the data I collected from the Global Energy Observatory, solar PV was producing power 11.4% of the time across the calendar year. Wind was producing power 24.9% of the time in the year of 2018. As I understand it, engineering has increased that to 33%, but that is still under par. So we need a buffer. I had to make some assumptions. I had to start somewhere. I thought I was using a very conservative number. In the literature, there were 2 references I could find. One was 48 hours plus 10% in 2012. Clearly, that will not be enough. Then Drost Frank in 2015 recommended 1 month for the whole system. I picked 4 weeks just for wind and solar. I believe the real number will probably be larger. When I presented this information to an energy company that runs wind turbines in Finland, they said 4 weeks was probably conservative but not outrageous. A real number, a more practical number that is more manageable is something like 3 weeks. All right, so let's use 4 weeks and 48 hours. So 72% of the power grid, if we were to incorporate wind and solar, non-fossil fuel systems, is about the size of the existing power grid as it stands. That's huge. Can we even balance such a large system? So 4 weeks is about 2,000 terawatts, 48 hours is about 158 terawatts. We do need a power buffer, and it does need to come from somewhere. Why batteries though? So here is a roadmap study done by the Singapore government. This was actually sort of done and compared, and they looked at a whole series of technologies: flywheels, supercapacitors, batteries, compressed air, pump storage, and they balanced everything up in terms of, blue is the more favorable. supercapacitors were limited by the time of power storage required. They believed and came to the conclusion that the power grid storage had to be a battery bank of some sort. So here is the engineering applications. So compressed air had problems in engineering scale up and also flexibility in application. Pumped hydro storage is how most things are done at the moment. Finding new geographical sites in large enough numbers is going to be a problem. So battery banks were believed to be the solution because they could be installed quickly in any geographical location, in any weather conditions. And allegedly they were cheap. So the United States keeps about 6 weeks of storage in the form of chemical fuels during winter and heating. So let's say we reach $200 a kilowatt for a battery. Then a $200 trillion worth of batteries can only provide 10,000 terawatts of energy storage or 3.4 quads. As the US uses 92.9 quads for primary energy across the calendar year of 2020, that's about 2 weeks storage. And it's not enough to heat homes in winter. So large-scale heat storage and nuclear generations are probably needed for 100% energy infrastructure. A game changer could be is if we could synthesize liquids efficiently. Also note that the 8 hours of energy is a colloquial term to show scale and contrast in primary energy use. But if it's normalized to just electrical energy use, it's more like 60 hours or 2.5 days. There have been other studies. So this was a, back one. So this was a study that was looked at power storage. This was Wei et al. Empirically grounded technology forecast for energy transition. They predicted by the year 2060, the dotted line is available storage capacity. They've got estimates of 50,000 terawatts or 6,000 to 7,000 terawatt hours. So my paltry 2,000 terawatt hours is really small in comparison to other studies with these long range transformations. So power storage, where are we at? Wind and solar is really variable, but it's variable over long periods of time. And currently systems are balanced by external grids, often using fossil fuels. And to date, wind and solar power grids have been effectively, relatively small. How are we going to balance such a large grid with 70% of the power? I don't think anyone knows how to do that yet. Strategic planners do favor the use of battery banks in some form. And the technology to buffer long-term seasonal variations in the volumes needed may not yet exist. The size of the required power buffer is still unknown. I've used 4 weeks and 48 hours, but the real number is probably something in between. Now, batteries aren't going to be the only answer, obviously. They're going to be a big part of the answer, though. There is a sensitivity, a set of questions that can be discussed around this, what will work and what won't work. What was the role of energy return on energy invested in my calculations? Well, this is a blunt instrument. There is little agreement in the literature of how this should be calculated. In my work, I've actually sort of quoted some studies that were done a few years ago. So what's included in the calculation? How far should the analysis go? It's a blunt tool. It's very difficult to ensure that systems like coal and solar power and nuclear power are compared appropriately. So I'm recommending that until we get some sort of agreement that we shouldn't use energy return on energy invested in the calculation of what we are doing going forward, until it's reinvented. Work is being done to try and do that, but we're not there yet. For this study, all calculations were based on the straight replacement for the calendar year of 2018 of the industrial system to do the same physical tasks. Energy return on energy invested was not actually used in those calculations. Kiitos.